Hello, everyone, and thank you for joining us today. My name is Kim Middleton, and I will be your host for this NASA Technology Transfer Program webinar on NASA's fiber metal laminates made by the VARTM process, VARTM. Our presenter today is Dr. Brian Jensen. Dr. Jensen is NASA's Senior Researcher for Advanced Materials and the Deputy Technical Fellow for the NASA Engineering and Safety Center Materials Technical Discipline Team. He has been employed at the NASA Langley Research Center in Hampton, Virginia since 1980 and is currently working in the Advanced Materials and Processing branch. He received a BS degree in chemistry from Randolph-Macon College in 1980, an MA in chemistry from the College of William & Mary in 1983, and a PhD in chemistry from Virginia Commonwealth University in 1990, specializing in organic and polymer chemistry. Dr. Jensen's duty involved the development of new high-performance, high-temperature resistant polymers and composites associated novel processing methods for advanced aerospace applications. He has worked in several areas, including composite matrix materials, adhesives, flexible high-temperature resistant insulations, and metal organic hybrid materials. He has almost 200 publications, 31 U.S. patents, and 53 commercial licenses. He's received several awards, including the NASA Exceptional Achievement Medal, 2 NASA Commercial Inventions of the Year, one in 1998 and in 2008, an honorable mention as well in 2018, an R&D 100 award, the NASA Exceptional Service Medal, and is a member of NASA's Inventors Hall of Fame. Following Brian's presentation, I will be giving a short presentation on how NASA licenses technologies to outside organizations. Before we get started, I'd like to point out that your microphones will be muted throughout this presentation. So if you have any questions, please type them in the chat box in the lower right corner of your screen, and we will answer them during the Q&A session at the end. At this point, I'd like to turn the presentation over to Dr. Jensen.
Thank you, Kim. I appreciate the introduction. I'll put my video on briefly here just so you can see who I am, and then I'll cut it off in case we have some bandwidth issues. But just wanted to kind of show you what I look like, and I am that old. I did start at NASA 42 years ago, so I've been here a long time, and the majority in this office I'm sitting in right now. So anyway, I'm going to cut the video off now in case there's some bandwidth issues and start with the presentation. As Kim mentioned, today's presentation is titled Fiber Metal Laminates Made by the VARTM Process. That's Vacuum-Assisted Resin Transfer Molding. I want to start off by recognizing my co-authors, Roberto Cano, Steve Hales, and Joel Alexa. Bert and Steve are NASA employees also here at Langley in Hampton, Virginia. Joel Alexa is an on-site contractor we have with Lockheed Martin Engineering and Sciences here in Hampton. Next chart, please. The problem as we see it for these types of materials, or this what we believe is a solution, is the current manufacturing process for fiber metal laminates requires prepreg and then an autoclave or press. The part size is limited by the size of the autoclave or press, and the process itself is expensive. So our goal is to try to solve some of these cost and size of manufacturing issues. Next chart. So we can hopefully reduce the cost of fiber metal laminates by removing them from the autoclave or from these presses and manufacturing them by the vacuum-assisted resin transfer molding process. Ultimately, our goal is to produce FMLs with a level of quality compared to GLARE. GLARE is a commercial material manufactured by autoclave, and it's an extremely high-quality material, and I'll talk a little bit about that and how our materials compare to GLARE. Next chart, please. I should be able to get through this presentation in 20 or 25 minutes, so we should have plenty of times for questions. So I'll kind of keep the time frame in mind and leave time available for questions. Outline is shown here: fiber metal laminates, composites processing by VARTM, VARTM processing of these fiber metal laminates, metal plasma coating process that we used, and then VARTM of the metal plasma coated fabrics, and then I'll summarize. Next chart. This is a chart that shows what GLARE is. GLARE stands for glass aluminum reinforced epoxy, and it is a type of hybrid laminate that's comprised of thin layers of aluminum alloy alternating with glass fiber reinforced epoxy. There's a number of commercially available GLARE grades, and some of them are shown here on the left side: GLARE 1, 2, 3, 4, 5, and 6, for example. Different alloys and different thicknesses of those alloy layers can be utilized. Different orientations of the glass fiber and thicknesses of the glass fiber can also be utilized. So you can see there's a number of options to tailor GLARE, the composition of GLARE for a particular application. The next chart, please, shows some photomicrographs of GLARE. Upper left is just cut with a bandsaw, milled side view and picture B, and then the kind of cleaned up sanded view and C. You can see the shiny layers are the aluminum layers, aluminum foils, and the layers between are the glass epoxy. You can see it's a very, very high quality material with no voids and exceptional wet out and bonding. So the materials we're developing are competing against let's just say a very high quality commercial grade material. Next chart, please. Some of the applications of GLARE are shown here. It's used on the crown panels for the Airbus A380. Also used in floors and liners and different structures like that. Also, GLARE is used as a impact or blast resistant material for cargo containers. The container you see on the right was designed to contain the blast of the Lockerbie bombing. Not sure how many people would remember this, but in 1988, terrorists put a bomb on a Boeing 747, and it exploded in that 747 over Lockerbie, Scotland. It brought the plane down and killed all the passengers. So there was a significant effort to try to develop cargo containers that were both lightweight and could contain blast from potential bombs. So that's an example of a GLARE structure that was able to contain that blast. Next chart, please. So GLARE characteristics in general, compared to the metal, the strengths are increased modulus, improved fatigue resistance, and lower weight. The fatigue resistance and lower weight, obviously, due to the composite material itself. Strengths versus the composites include improved impact resistance and damage tolerance, improved permeation resistance if the materials were used for gaseous tanks, for example, and increased load-bearing ability. So GLARE tries to, let's say, utilize the advantages of both the composite and the metal. GLARE itself, though, is only useful in subsonic applications because of the temperature limitations of the aluminum and the epoxy materials. Next chart, please. This is a setup of VARTM, vacuum assisted resin transfer molding. The way the process works is there is a composite preform that's shown as an arrow pointing from preform into the diagram. There's a dry composite preform, usually stacked layers of fabric material are placed in on a tool. There is what's called a flow media that is cut to lay over top of the preform itself. with about an inch or two gap between the outside of the preform and the flow media itself. Resin is fed from a resin bucket. It flows through the flow media, pulled essentially by a vacuum pump, and then it flows through the thickness, down through the flow media, through the thickness of the preform. The next chart shows a little bit better description of how that works. If the infusion was only along the direction of the part itself, it would take an extremely long time. So the flow media allows the resin to flow through the thickness and make the part in a much quicker process. So this is a side view of the process itself. You can see the flow media is depicted there in orange and yellow. The metal foils are in blue, and then the preform or fabric material is shown in black. What we've done essentially is we've inserted small holes, we'll call them resin pathways, into the metal foils. The resin flows through the flow media and then through the thickness, through the holes in the metal foils, wetting out the preforms and then subsequent layers below. When the part is fully infused, the resin pot is closed, the vacuum is closed, and then it's cured just by a standard oven process. So there are very few size limitations to this process as long as you have a part large enough and enough resin itself. You can make very large parts and you aren't limited by a press or an autoclave. Next chart, please. So obviously the holes in the foils are flaws from a mechanical point of view, but these flow pathways, these holes can be extremely small. You can see the photomicrograph of one of the materials. We were able to essentially get a section that showed a flow pathway or a hole, and then you can see compared to the dime on the right-hand side, these holes are extremely small. We were able to space them at about an inch apart. So there's a rule in apparently in holes in metallic structure. If the holes are more than 4 diameters away from each other, they act independently. So even though there's a lot of holes in these foils, they act kind of independent of the other ones. So the damage is really limited to the size of the hole itself. It's not it wouldn't be viewed as a overall damage from having the multiple holes in these small foils. So this just is to show you that the holes themselves are very small and spaced fairly far apart. Next chart. We did a little bit of testing. I have to admit that most of this work was done without a great deal of programmatic support. So we're kind of on a shoestring budget. So most of our work was trying to develop the, let's just say, the experiments that would allow us to patent the process. And we weren't able to spend a lot of time generating mechanical property data. But the one thing we did was wanted to understand the essentially the damage caused by the holes in the aluminum foil. So this is some specimen we tested on fatigue resistance, cycles to failure of different foils themselves with different size holes and spacing. And I point to the bottom of the second column, the mean number there, 9,800 cycles to failure for a foil that has 0.4 millimeter holes and 1 inch spacing. And then across the right-hand side, second column from the end on the right, the no holes straight is the top of the column. The number there is 20,983. So essentially the holes cut the cycles to failure in half compared to what would be considered a pristine sample. There's a lot of edge effects in real thin foil cycle fatigue. So it's these numbers, I guess, should be taken with a little bit of grain of salt. It's the edge effects can make a big difference, but there is some reduction in properties for putting the holes into the foils. Next chart, please. The next chart shows a FML fiber metal laminate that was exposed to fatigue testing. You can see that the fatigue cracks do initiate around the holes within the material itself. So there is a reduction in fatigue properties. We were, let's just say, we went into the work understanding that there would be some reduction in fatigue, but we also realized there were a number of applications that weren't fatigue property driven, like blast containment, for example. So our focus really was on non-fatigue driven applications for these types of materials. Next chart. The method for putting the holes into the foils makes a significant difference. We tried a number of different processes. We used a small Dremel drill, we used a water jet, we used lasers actually to essentially burn holes in the foils, and then learned a little better job doing some precision drilling. The next chart shows a picture, a close-up picture of the inside wall of two different holes done by two different processes, Dremel drilling on the left side and precision drilling on the right side. The fatigue properties are almost completely driven by the quality of the hole put into the foils. The higher quality of the hole, the better the fatigue resistance is. So these materials, again, we did most of our work just trying to capture the patterns on these materials. We weren't able to do full characterization, but we did learn that as long as the holes were spaced fairly far apart, more than 4 or 5 diameters from each other, and if the holes were high quality and didn't have a lot of, let's say, texture or roughness around the edges, then the fatigue properties weren't as bad as one would expect. So next chart, please. So that is the kind of the first type of fiber metal laminate that I wanted to talk about. The second type that we did involved depositing metal onto fabric. We have a piece of equipment at Langley called a RF plasma deposition facility. We use radio frequency energy to form a plasma. We can then take metal powder of essentially any choice, put it insert it into the RF plasma. It melts and then is accelerated along the direction of the plasma. And you can see from the equipment there that in the window, you can see the plasma through the window itself. Next chart, please. Inside that equipment, we have a drum that's about 18 inches across and about 3 foot circumference. That drum will translate and rotate around an axle. So we can take fabric, wrap around the drum, and then translate and rotate under the plasma itself that has the molten particles, and we can coat the fabric that we have on the drum. And that next chart shows kind of partway through the process where we have some layers that have been, some metal that had been coated on, and then the next chart actually shows the final material that's made by this process. Now the parameters for the deposition process can be controlled if you use a very small particle size metal and use let's say a hot plasma. You can fully melt the metallic particles themselves, and they'll form essentially a densified layer on the fabric. If you use larger particles or use, let's say, less energetic plasma, you can just melt the outsides of the particles, and you can get essentially a porous material that's formed on the fabric. Show the next chart, please. Shows the results of what we were doing. Well, here's an example of copper on glass, for example, on the right side, and then aluminum on carbon. Obviously, you have lots of choices with either of these types of materials. You can choose different metals, different fibers within the fabric, different fabrics. And then in the infusion process, you can obviously choose different matrix materials. So the next chart, I believe, shows the process. Well, another example of materials that we've made. Here's 3 larger samples of the metal coated fabric just to show you the dimensions. It's about 1 foot wide of coated material and about 3 feet long. That's just to show you the scale we were working at. Again, our goal was to make enough material to develop the process and obtain the patents. Next chart now shows the layers that we got by using a particular process with some chosen parameters. You can see the metal coated material is on either side of the fabric. For example, here we coated both sides of several different fabrics. We set the parameters of the deposition process so that we only melted the outside of the particles and didn't fully melt the particles. So we were able to put a porous layer of metal onto the fabrics. That allowed us to then infuse through that porous layer. What you're seeing here is one of the earlier versions. It's not a very high quality coating or very uniform coating. The next chart shows a material after we got a little bit better at the coating process. Again, we were able to set the parameters so that the metal layers were porous and then would be receptive to the VARTM process. Next chart. This is an example of I believe we used 4 layers of metal coated fabric here, and then did a VARTM infusing to make the structural material itself. We were able to get high quality by this process. So the next chart, please. Okay, the quality of the part was very good, kind of similar to the glare type materials. We had essentially 0 void content, and all the voids in the metal were wet out as well. One of the advantages of this process is there are so many options to work with, and the materials can be tailored for specific applications. There's a number of options for the materials themselves. You can choose different fibers: glass, carbon, Kevlar, for example. Choose different resins from epoxy to polyimide and other types of resins, and then metals. So there's a very large design space here that can be utilized to meet the needs of a desired application. The process itself that also has some variables: the resin pathways that we put into the foil materials, the size and the pattern can be varied. The plasma coated metal layers, the thickness can be controlled. The texture, you can coat on either one side or both sides of a fabric. You can make the metal coating either more or less permeable depending on the process parameters. And then within the laminate itself, you can change stacking sequences and number of plies. You can vary the metal to composite ratios, and also obviously different preform types can be utilized. So there are a lot of variables that allow tailorability for desired applications with these types of materials. Next chart, please. So to summarize, we successfully fabricated fiber metal laminates by VARTM. We utilized both metal foils and plasma metal coated layers. We evaluated flow pathway insertion methods and the effect of those different methods on hole quality and resulting mechanical properties. We demonstrated plasma coating of aluminum, titanium, and copper onto fabrics. In fact, we also used tantalum. There's a desire to build radiation shielding type materials for spacecraft. So we used some high Z elements as well to make radiation shielding type materials custom made. So we've also used tantalum as a deposition metal. Used glass and carbon fabrics. We have used a number of different plasma coating parameters, and they can be optimized for density, for example, of the metal coated onto the fabric. And we did do some kind of crude testing of the plasma metal to fabric bond strength. We tried to measure the bond strength, and in essence, when we pulled the metal away, we just tore part of the fibers off of the fabric. So there appears to be a pretty strong bond between the metal and the fabric itself. So we have been developing VARTM process models for fiber metal laminates, and they are very similar to the standard VARTM process models, but they have been developed or under development. and we have been able to introduce some complex shapes at relatively lower cost compared to presses and to autoclaves. Some of the applications, this is the last chart I have, I believe. Some of the applications, again, I mentioned are probably designed for non-fatigue driven properties. So that would be blast containment, say permeable or reduced permeability for gaseous containers. Lightning strike protection was one property that we were looking for, and we did test for copper on glass and building composites from that and the ability to protect for lightning strike. Current aircraft use a astro strike material that's expanded copper that's placed on the outer layer of a composite after it's built. This would provide a method to put lightning strike protection within the composite itself and kind of build it into the structure instead of having to set it on to put it on later. The ability to put metal on composites also can provide some interesting properties for things like turbine blades. Turbine blades are subject to a lot of erosion just over long periods of time. And the ability to put a metal on the leading edge of a turbine blade to try to help reduce erosion, for example, would be useful. So while we understand there is some reduction in mechanical properties by putting holes in the foils and also by having voids in the metallic layers put down by the plasma deposition process, there are some non-fatigue driven applications that could benefit from these types of materials. And with that, I'll stop, I believe, and answer questions.